say thank you for everybody attending, and here we are in session 2. Just a very short recap. Session 1 just sort of introduced you to the basic concepts behind deep learning. We did it with a deep neural network, which is, those are the linear layers or just nodes, so it's before a convolutional neural network. Did some introduction to TensorFlow Keras, the sequential and the functional API. And then right at the end, we covered a little bit about doing simple images like mints in a deep neural network. As you might guess, we pointed out the parameter explosion if you try to do large images, and that's where convolutional neural networks come in. They're far more appropriate the moment you get into any real-world images, and that's what we're going to talk about today. Okay, so the simplest way to think about a convolutional neural network is to think about it as if it's a front end to an existing deep neural network, okay? And we're trying to solve a simple problem, okay? And the problem is the number of parameters. So if you remember with mints, we were it's a grayscale image. That means it has one color plane or a channel. 28 by 28 is 784. So this vector coming in is only 784 pixels or weights, okay? The problem if you get to a real world image, like a megabyte image, 1024 by 1024, well, instead of having 784 elements in a vector, you'd have 1 million, and that would just explode, okay? It would make the deep neural network unusable. So the goal of a convolutional neural network is basically to find a different way to reduce those parameters substantially, okay, such that by the time you get down to what we call the classification learning, this 1D vector is a more reasonable size. And it consists of a handful of stages. So some of those stages are called convolutions, which we'll go into more detail. And they're about converting in TensorFlow Keras convolutional layers. You have to specify the number of channels. So even though it's a single channel, I can't say 128 by 128. I have to go 128 by 128 by 1. Yeah, at this point, does anybody have a question? Okay, I'll continue.
I got a question.
Oh, good.
Yeah.
I like it.
What happens? So for a grayscale image, you're using a channel of 1. What happens if you use a color image and still use a channel of 1 here?
Oh, it wouldn't match, and it would throw an error when you try to train or do inference, or just say mismatch shape at the input layer.
Okay, all right. It'll throw you an error. That's good.
Yeah. But just to show you, if this was an RGB, that would be a 3.
Okay.
Andrew.
Yes.
All right.
I have a question. So basically, your input shape was 128, 128.1. That basically means the image size is 128 by 128. Is it?
Correct. And there's only one channel, which would be a grayscale image.
I see. So it is actually a very small image. I mean, normally the image will be 1,000 by 1,000 by 3, normally something like that, right?
Yeah, but if you recall, much earlier, we found that convolutional neural networks, when it comes to image classification, can do extremely well all the way down to like typically 224 by 224. So if you had a megabyte image, 1024 by 1024, upstream from this, and I'll show you there's a section later, I'll show you how we do that. We would upstream here, we would resize or the image to a smaller size.
I see. Thank you.
Question, is this always generally the same for all applications, say for medical or?
No. Okay, so for object detection, the ideal size tends to be around 600 by 400. And you might ask, oh, why do we need it such bigger? Okay, Well, okay, in image classification, we're using the whole picture, right,
Yeah.
to say what's in that picture, one item, right? What is it? It's a
Right.
dog, it's a cat, a horse, or whatever. In object detection, we're cutting up the image and we're looking at different places in the image and saying what's in that place. Okay. And so what happens when you have small objects? You have a lot less pixels to work with.
Mhm. Right.
Okay, so what they found is for object detection to work well, you need to work with larger images. Okay, now when you get to medical images and you're doing image segmentation, you're trying to look at cells and trying to look at different parts of the cell and say how cancerous this is. Yeah, you need even larger image input.
Okay. Okay. Yeah. Yeah. Good. That was my basically my question on that, the application.
Okay, yeah, but these sizes have been found, over the years by researchers and become best practices.
Can you have more than 3 channels?
Yeah, you could. The think of it this way: to the convolutional neural network, it has no concept what an image is. It's just creating features and extracting them. So you could have some um, synthesized representation of the world. Let's say you had some gaming engine that created some kind of synthesized image that to a human would mean nothing, and it's multidimensional. It's got 17 dimensions. Okay. Yeah, you could have 17 there.
Okay, thank you.
Yeah. Um, okay, so I think we're ready to go. The next slide. This thing is messing with me for a minute.
Hey, Andre,
There we go. Okay, yes.
just a quick question, since you mentioned how could H be 17? Normally H will be 3, represent you 3 different colors. How could it be 17? Just
Well,
to
remember that RGB is just simply a format representation of an image for the purpose of rendering it on a monitor. And monitors work, technology as RGB. Okay, there are other color spaces that are really ideal for, say, printing, that have more channels, 4 or 5.
okay.
So, so RGB is just an arbitrary representation that was designed for the hardware of originally for cathode ray tubes.
Okay, thank you.
That right. Okay, so we showed you the first convolutional layer, right? Okay, so the next thing I'm going to keep this real simple. Next thing we want to do is, of course, is now we want to reduce those feature maps we generated. We generated 16 of them. Hey, let's make them smaller. Okay, each one 1/4 of the size, and then we got to flatten them, right? Before we go into our backend DNN. I kind of left out the ReLU here. So after our convolution, we put it through a rectified linear unit as our activation function. Now we go to max pooling. Okay, so here we're going to set the pool size as 2 by 2, and we're going to set the strides to 2 by 2. So it's going to go every other pixel as it moves that window. Okay, and because it's max pooling, that means we're going to take the maximum value of this 2 by 2. So that's a 4-pixel square. So we look at those 4 pixels, which one has the highest value? That's what we're going to replace it with. Because our stride is 2, the output will be 1/2 the width, 1/2 the height, which actually will make it 1/4 the size. Okay, and notice we don't have an activation function here, and it's because we don't need to. This isn't a learn layer. This is a static algorithm. Okay, so there's no parameters in it. Okay, and then finally we take the output of those reduced or pooled feature maps and we're going to flatten them. Okay, so I notice if I'm clicking in there, that's why the arrow doesn't work. Yeah. got some kind of in this mode. My arrow is kind of hard to work. See if I can give me a moment. There we go. Okay, there we go. So now it's time to attach the DNN classifier. Okay. So in this one, hypothetically, I'm going to say, think of it as the DNN has its own input layer, but the input to it is the output of the convolutional neural network. So the input layer here, I'm going to say, is 512 nodes. Here's the activation function. No hidden layer, just go straight to an output layer. In this example, I'm pretending those 128 by 128 grayscale images was actually a handwriting or hand signed characters. Uh, yeah, sign language. Actually, I did this a long, long time ago when I was first learning, I had a data set of grayscale images of the hand doing the hand signing this 26 characters of the English language. And that's what this one was learning. Okay. And then finally, of course, your activation function. And since this is a multi-class classifier, we would use a softmax. Then we got to compile it. We specify our loss. How do we calculate the loss between what we predict and the actual ground truth? So we'll use the categorical cross entropy. Again, in general, the best practice for that as an optimizer is Atom. So I'll pause for a moment if anybody has a question.
Yes, I have a question. I mean,
Okay.
is there an intuition of when should we use a max pooling or average pooling?
We're going to get into that later in the training.
I see.
Right now, I'm just sort of introducing you to the concepts and doing what's called simple covenants. But yes, absolutely. I'll be getting into the best practices. Okay. So let's also take this model we built. It doesn't look like that big of a model, right? Let's just go back here. We have an input layer, 16 filters, right? 128, 128 coming in. We max pool it. We flatten it. We have a dense layer of 512 and an output layer 26, one for each letter in the alphabet. Let's do a modeled out summary and let's see what it would look like. Okay. So first, actually, it's quite a lot of parameters. 8 million parameters. Wow, that's a lot, isn't it? Okay, they look pretty small. So let's kind of look at the input here, the output shape, and it looks a little different. If you remember when we were looking at a DNN, the tuple was just pretty good timing here. So yeah, our timing's right on. So again, this one we have a little lab here for you guys to do. So just like last time, I encourage you guys to click on it. And if you run into any problems, just I guess you say wave your hand. But before we leap in the lab, are there any final questions on this?
So to improve accuracy, we can combine both batch normalization layers and dropout layers. We can combine them in the network.
Yeah.
To get
I mean, it's a
better
convention
accuracy.
today. Any whether it's a deep neural network or a convolutional neural network, you will look after every layer that has parameters, a kernel. You'll see a batch normalization paired with it.
And for the dense layers, we can use the dropout?
You usually only use a dropout at the very end before the dense layer that you do the classification.
Okay, okay, good.
Andrew, it sounds like many of these models are open source, or at least teams are able to improve on previous work because they have access to the information, to the code.
Yeah.
Are there any models out there that are actually proprietary that are known but are not necessarily disclosed to the public?
Well, of course, I mean, if you think about all these big enterprise companies, that have, that's something out there that they generate revenue from, You know, that's kind of like their the crown jewels. Of course, they're not. They may write papers about them and describe them, but the source is not available.
And are possibly better than the public ones?
To some extent, possibly. I mean, the way I look at it is, say a company spends $20 million to come up with a great model for a particular purpose that makes them a lot of money. Okay. Yeah, for maybe a year or so, they have an edge, but you know, public research eventually will overcome it. It's like a war, it goes back and forth.
Got it. Thank you.
Anybody else have a question?
And can one with the personal computer hope train such a model on his personal computer, or it really takes a huge amount of computer resources?
Well, today's models, we have this concept of a compact model. Okay, so different type of model design. Okay, they're computationally small enough that if you got a laptop that's got a GPU on it, yeah, you can train it.
Okay.
Yeah. But you know, if it's something that's really, but that's, you know, compact models really fit a limited area. I mean, they're good at things like image classification or object detection. But if you were trying to do like a chat bot and you needed to use a transformer or a BERT type natural language processing model, which is a billion plus parameters, yeah, you're not going to train that on your laptop.
Okay. Thanks.
Hey, Andre.
Yeah.
I'm just trying to repeat what you said to make sure I get it correctly. So basically, the main reason for the convolutional network is to reduce the number of parameters that the computation needed. Is that a correct comment?
Yeah, that's a correct comment. I could phrase it a different way. If without it, a deep neural network is learning pixels. Okay. And with convolutions, we're learning features. So what the convolutional front end is looking at all these pixels as if they're entropy. Most of it is noise. Okay, that's your entropy. Okay, and reducing it to just features. That's your information gain. And with those features, that's what goes into the deep neural network to do the task learning.
So basically, after the convolution, as you demonstrated, there has a flat layer, which basically flat everything into one dimension, and things go from there, right?
Yeah.
Okay. Thank you. By the way, a follow-up question. So when you flatter it, do you actually losing the how to say it, the dimension information, or you actually don't?
Oh no, yeah, you've lost the dimensional information.
But you are confident to flash it, and it's working fine.
Yeah, because because now it's just like a bunch of signals. You know, you're not learning any you don't need any spatial information anymore because you're not learning any features anymore. You've already extracted all those features. Just throw in some terminology a little ahead of time. When you get to those last feature maps, those tiny little feature maps, okay, that's called the latent space of the model. Okay. And the latent space is just saying is you found a representation of a high dimensional input into a low dimensional input.
I got you. One question. So for the filters, the model itself will actually design those filters for you. It sounds like you actually you don't have control over the filters.
Absolutely, it learns the filters. Put us all imaging scientists out of work who used to hand design these, just like me.
I have a question. So,
okay.
Going back to someone said about training on a laptop, and you mentioned models like BERT with 1 billion parameters can be trained on a laptop. So what is the primarily, is it the number of parameters that determines required resources?
Yeah, the parameters is the biggest one. Also, the size of your data or batch, how much you can hold in the memory to feed into your model. Okay, so those are the physical constraints. It may be just because of the size of the model or the size of the input data physically you can't train on your laptop. Now, and maybe you have a model that, okay, both the size of the model and the size of the input fit fine, but the amount of data needed to train it might take days or weeks on your laptop.
So what's the solution? Is it like a
Well, that's when that's when enterprise companies go to the cloud.
So it would be a cluster in the cloud. That's what.
Yeah. It's a virtual cluster of provision instances consisting, typically of GPUs.
Okay. Will you talk about this a little bit later on, like the requirements of training?
Yes. Well, actually, on our third session, we start on training.
Okay, great. Thank you.
But can the workaround for that be the transfer learning, where we reuse already pre-trained, existing pre-trained models, and we just plug our network?
You just replace what's called the top end, which is probably you might think is the bottom. That very last